This is an introduction to VLSI design course, and today we will talk about circuit pitfall. This talk is divided into two parts. First, we will talk about some subjects like the following: variation and noise budget, reliability, and then the second part we will check some example where you have circuit pitfalls and how to solve their issues. So let's start with variation. What we mean by variation is when you have differences between, for example, transistors that are fabricated the same way, but for some reasons they are slightly different than each others. We will talk about the process corners first, and then we will see the process itself and how it is affected by the threshold, by the channel length and the interconnect dimension. Also, we'll see external reasons like the environment, voltage and temperature, and also the aging and the wear out. And that will be the first part of this lecture. So the process corners, it modeled extreme of process variations in simulation. As you can see here, we have NMOS and PMOS. It could be slow and fast, and we have four different corners with the typical in the middle. The corners are either typical T, fast F, or slow S. And the factors, actually the NMOS speed, the PMOS speed, the wiring, the voltage, and the temperature. And in this table, you can see some examples. For the corner fast, in the voltage is 1.98, the typical is 1.8, and for a slow corner is 1.6. In the temperature, to be fast, you get 0 degrees centigrade, typical is 70, and the slow is 125 when you have a very high temperature. And you can do the same for many other factors. This table is actually showing you the corners, the setup for each one of them, and what is the purpose. So for example, this one here, the NMOS in the slow corner, the PMOS in the slow corner, the VDD in the fast corner, and the temperature in the slow corner, you do this for the dynamic power. So circuits are simulated in different corners to verify different performances and correctness specification. And you can read the rest of this table. That's the purpose of the corners. Now, when we talked about the process variation, here is three main factors into this. The threshold voltage. It depends, you can see it here in this figure, and it depends on the placement of dopant in the channel. The standard deviation, inversely proportional to the channel area, as you can see here. This is the standard deviation, and the area is in the denominator. So the thing is, if you have two transistors fabricated the same way, it's based on the doping. The doping will be definitely a little bit different between both of them. And this is why we will have different transistors. The change or this process variation should be tiny, very small. The channel length is actually systematic across chip line with variation, or the ACLV, random line edge roughness, LER. These are subjects that are very interested when it's related to, or it is actually directly related to the channel length. You can read about them in your book. For the interconnect, etching variation affects all the dimension, the width, spacing, the height between layers, and so on. Now for the spatial distribution, variations show actually spatial correlation. If this is the die with the set position X and Y, and this is the frequency to see the variation in transistors. It could be from lot to lot, or wafer to wafer, or die to die, or what we call inter-die. or within a die or intra die. The thing here is closer transistors match better. So if you take a special region here, the transistors that are there match better, and so on. For the environmental variation, like the voltage and the temperature, the voltage, as you can see here, we have the X, Y, and we have the variation percentage and the vertical line. So the VDD is usually designed plus or minus 10%. We have regulator error, on-chip droop from switching activity as well. And because of this, we have the variation. And you can see, for example, we have variation here, it's sinking down, it's peaking up at this region. So there are slight differences. In the temperature, the ambient temperature ranges, and we said that on the table before. And this one, like for the standard of this commercial, industrial, or military, the minimum for the commercial is 0 degrees centigrade and the maximum 70 degrees centigrade. In the industrial, we are having more range. In the military, even more range. It's because of the application itself. On-die temperature elevated by chip power consumption, of course. The places where you have a lot of heat is actually the same places that consumes a lot of power. Now for the aging or the wear out. Transistor changes over time as they wear out. Reasons for this, the HCI or the hot carrier injection, the NBTI or the negative bias temperature instability, or the TDDB, the time-dependent dielectric breakdown, or the electromigration. These four main reasons affect the transistor age. Usually it causes threshold voltage changes. We want the threshold voltage to be as less as possible. Usually they have or causes the threshold voltage to change, increase, probably not stable, and so on. So let's start with the hot carriers. The HCI, it's caused by hot carriers, and that's because of the field between the source and the drain. So the electric field across the channel impart high energies to some carriers. These hot carriers may be blasted into the gate oxide. So because of collision, they can hit the gate oxide and get trapped there. So as we said, these hot carrier may be blasted into the gate oxide where they become trapped. The accumulation of charge in oxide over time causes shift in the V threshold over time. Eventually, the V threshold shift too far for a device to operate correctly. So choose the VDD to achieve reasonable product lifetime. Worst problem for inverters and NORs with slow input rise time as long propagation delay. Now we will move to the NPTI or the negative bias temperature instability. Again, it's an electrical field. So there is an electrical field that applies across the oxide, which means that it is in the vertical direction. This forms dangling bond called traps at the silicon to silicon oxide interface. Again, the accumulation of traps over time causes the V threshold again to be shifted. Most pronounced for PMOS transistor with strong negative bias when the VG is equal to 0 and the VS is equal to VDD at high temperature. And this equation is the dominating equations for the NPTI. For the TDDB, the time-dependent dielectrical breakdown, it's actually a gradual increase in the gate leakage. The gate is not supposed to leak any current. However, we talked about this in the non-ideal transistor theory. We have actually some small leakage. Over time, this increases. It gradually increases in gate leakage when an electric field is applied across an oxide. Again, it's the vertical electrical field, also known as stress-induced leakage current. And if this leakage kept gradually increasing, at the end, it breaks down, and the transistor breaks down and becomes an error, and actually it should be thrown away. For 10 years life at 125 degrees centigrade, you should keep the electrical field at the oxide below 0.7 voltage for every nanometer. The electromigration is the reason of the open circuits over time. We call it electron wind, which causes the movement of the metal atoms. The metal atoms themselves, they are moving along the wire. And as they move with time, we're talking about years sometimes, they start causing an open circuit. So excessive electromigration leads to open circuit. Most significant for unidirectional DC current, and it's depending in the current density and also exponential dependence on the temperature, as you can see here in this equation. And you can see this video to see how it's working, the electromigration over a very long period of time. For example, here between V2 and M2, you can see this crack as actually because of the atom movement, you have an open circuit here. Now, for the noise, there are so many sources that we talked about before. Some of the sources, the power supply noise, the capacitive coupling, the charge sharing, the leakage, the noise feed through, and so on. The consequences, it increases the delay for noise to settle out, actually. So if you have spikes, this means that you have more delay, less performance, and less speed. If the noise is too much, it becomes, or it advances from being a performance trouble to become a bigger problem, which will give you incorrect computation. And speaking about errors or incorrect computations, so basically, just to say it in short, the noise becomes errors. If too much, if you didn't solve this noise over time, this noise accumulates and cause troubles here and there and becomes error. So speaking about errors, we will talk about the reliability. We have two types of errors, the hard errors and the soft errors. And over time, we worry about, when we talk about the reliability, about the failure rate. In any chip or any transistor, it has an infant mortality where the failure rate has a specific value. It goes down. It's actually here now. It's useful operating life. You can see the failure rate is as low as possible. In the infant mortality, because it's just, it has troubles and we are fixing it. And at the beginning, when even in human lives, the children have a lot of problems that we need to protect them from. And after a while, you have a useful operating life. And then at the end, you start to having some wear out and aging effects. And this increases also over time. The hard errors could be oxide wear out or aging, and we talked about the four reasons for aging. Also the interconnect wear out, like electromagnetation. And we have the over voltage failure and the latchup, and we will talk about these two shortly. Also, there are soft errors. We will talk about it after we cover these two. Now, generally, we can characterize the reliability as the mean time between failure, or the MTBF, which will be calculated as the number of devices times the hour of operation divided by the number of failures. Or we could measure it as failures in time, or FET, which is the number of failure per thousand hour per million devices. Now, we will talk about these three. First, the over voltage failure. The over voltage failure, high voltage can blow out tiny transistors. That's the problem with having an over voltage at that node or transistor. It could happen from the electrostatic discharge, which is kilovolts from static electricity when the package bin are handled, especially when you are trying to work with them. You can see that human bodies, when they, for example, walk in carpets, they accumulate a static charge. The same static charge here could affect the transistors, and it could be very harmful to them. The oxide breakdown in a 65 nanometer process, when VG is around 3 volts, it causes arcing through thin gate oxide until it breaks down. Also, the punch through high VDS, again, all of them causes of the over voltage. The high VDS causes depletion region between the source and the drain to touch, and this leads to a high current, almost a short, a high current flow, and destructive overheating. Now for the latchup, is actually caused by the positive feedback leading to the VDD to ground short. We know that we shouldn't have a short circuit between the VDD and the ground. The latchup can cause this, and actually in the 1970s, it was a huge problem before it was well understood. So to understand it, consider this inverter, and we actually talked about this when we talked about the fabrication in the first video, where we have tabs here. Now the thing is, if you looked at the NMOS transistor, you have N followed by P substrate, followed by M in the N well, followed by P in the PMOS. And from this path, you can actually connect the VDD to ground, especially when one of the two bipolar transistors get forward biased due to the current flow through the well or the substrate. So one way to solve against this, actually, that was the model for the what's happening here. It's actually redrawn here. So we avoid by minimizing the resistance to body, or from of the body to the ground and of the body to the PD. So this way it goes there and not shorted between the VDD and the ground. So you use plenty of substrate and well tabs for that. And this is one of the reasons we have these two tabs. Also, we can use the guard rings. Latchup risk greatest when diffusion to substrate diodes could become forward biased, as we said. So we surround sensitive region with guard ring to collect any injected charges. Any charges that could cause troubles, we collect them by this ring. So the P plus, it has rings. These rings is actually N plus guard rings. And as you can see, you have N well over here. And this will be connected with VDD. Or in the N plus, connected to the ground, you have P plus guard ring, and you have the P substrate. So these rings will protect the P plus, and this one will protect the N plus diffusion. Now for the soft error, in 1970, DRAMs were observed to randomly flip bits. And that's actually one of the difficult errors to solve. Sometimes the error is shown, sometimes it disappears. This is why they call them soft errors. Ultimately, it was linked to alpha particle and cosmic ray neutrons. So for example, if you have an ion hitting the B-type silicon, if it hits this direction, and it could be that randomly hitting anywhere. So if it hits this direction, what will happen is, because the ion has a positive charge, it will attract the negative charge towards its path, and it will repel the positive charge away from its path. This could cause a bit flip. With time, it disappears, and the ion goes back to its normal, or the diffusions and the regions goes back to their normal place. So collision with atoms create the electron hole pairs in the substrate, and these carriers are collected on the p-n junction, disturbing the voltage for quite a while. One way to solve this is by radiation hardening or hardening techniques. There is so many hardening techniques. The radiation hardening reduce actually the software. It increases the node capacitance to minimize the impact of the collected charges, or use redundancy. For example, the dual interlock cell that you can see. So this is an ordinary latch. And now, just before the inverter, notice that we are protecting the D, and we are also protecting the Q from any outside connections. So when you fan out here, this inverter is actually will protect the remainder of the cell. Similarly, this inverter is connected to, or this inverter protect the remainder of the cell from any other inputs as they fan in. So we talked actually about this before, but this is an ordinary latch, and one way to harden this circuit against the software error is to use this dual interlock feedback. You can see that this connection here, which was already protected by this inverter, it's connected here, and you can see that it's connected in the PMOS to this region here, and this region is connected to the PMOS and the NMOS. And similarly, you'll find this is repeated to the PMOS and NMOS, and so on, to the PMOS and NMOS, to the PMOS and NMOS. And you have the right assist circuit as well. You can see that from here, it's connected to this path, and from there, it's connected over here. This way, you increase the node capacitance and minimize the impact of the collected charge if you got hit by an ion where a software error could happen. So this way we harden the latch. Now, after discussing the first part, we will move to the second part, which is the circuit pitfall. It's actually, we will treat it as a deductive puzzle. So you are given a circuit and a symptoms. You should diagnose it or diagnose the cause and also recommend the solution. So we have 4 parts: symptom, diagnose, you have the circuit, you have the symptoms, you have the diagnose or the principle that we should work with, and we should have the recommended solution. We will have a lot of bad circuits, and we will try to figure what was the problem with them. All these pitfalls have caused failure in real chip over the years. So it's very good to know some of these bad circuits. So in the future, when you face something similar or the same, you know, or you are aware of what is going on. So this is the first one. And the first bad circuit is, the circuit is 2-to-1 multiplexer. It was designed this way. And now the symptoms, the mux works when the selected D is 0, which means this one, but not 1. Or it fails at low VDD. We investigate and investigate. At the end, we say that the principle is actually the threshold drop. The X never raises above the VDD minus V threshold because of the degradation, and you don't have a PMOS. The V threshold is raised by the body effect as well, and the threshold drop is more serious as V threshold becomes a greater fraction of the VDD. So when the VDD becomes smaller, or the difference between them is very huge. The solution, use transmission gate. So add the PMOS in both of them and avoid the pass transistor. This way you won't have these symptoms. The second bad circuit is a latch. That was one of the earliest designs of the latch. The symptoms, you load a 0 into the Q. You set phi equal to 0. Eventually, the Q spontaneously flips to 1, from 0 to 1. If it flips from 0 to 1, meaning that the X is the other way around. Now, after investigation, we know that the X is having some trouble, which is actually the leakage. So X is a dynamic node holding a value as the charge or on the node. Eventually, the subthreshold leakage, that's one of the current leakage problems. We talked about the subthreshold leakage and the gate leakage and the junction leakage and the contention previously when we talked about the power consumption. And this could or may disturb the charge. The solution, make it static with a feedback, or build it the way we told you how to build it. You have two inverters back to back, and you have or you need to protect the D and also protect the G. Another way is periodically refresh the node. So if it is leaking, refresh it and make it one again. But it requires fast clock and not practical process with big leakage as well. Now the third circuit, we have a domino and gate. This is a domino and gate. And the symptom, the pre-charge gate, when you pre-charge the gate, Y equal to 0, then you evaluate. Eventually, the Y spontaneously flips to 1. You can see that the same problem, since Y flips to 1, and you find this very surprising, actually the problem is on the X, the one that is before the inverter. Again, the same issue, leakage. And one way to solve this is using a keeper. And we already talked about the keeper before. Since this is leaking and maybe the one goes down to 0, after the inverter, this one is actually going to be 0. It will fire up this PMOS, meaning it will become on, and now you can charge the X and get away or get rid of the leakage. Now the bad circuit number 4, which is a pseudo NMOS or circuit, you can see that they are parallel, and this is a pseudo NMOS. Now the symptoms here, when only one input is true, Y is equal to 0. So this is a node. If one of them is equal, or one of the inputs is equal to 0, like this one, if this is 0, there should be the value of X should be 0, and after inversion should be 1. So you expect a 1, but you find that it is actually 0. Why? You investigate. Actually, one of the problems or the principles that we need to worry about is the ratio. We need to make sure that it is correct. If it is failing, if we have a ratio failure, then the NMOS and the PMOS fight each other. The current here and the current in the pull up and the current in the pull down. And if the PMOS is too strong, NMOS cannot pull X low enough. And this way you don't have Y equal to 1. And the solution, make sure you get the right ratio. Make sure you get the right ratio, meaning the right sizing. And we talked about the sizing before and how to do it to make sure that the pseudo NMOS works correctly. Now, this is the bad circuit number 5. This is a latch. Now, you did the latch, but the problem is that this inverter here is weak. The symptoms, Q stucks at 1. So no matter what you do, it is always 1. May only happen for certain latches where input is driven by a small gate located far out. If that's happened, then Q becomes stuck at 1. Again, the principle here is, as you can see, there is a difference in ratio. So it's a ratio failure. The series resistance or the D drive, the wire resistance, and the T gate, the time of the gate, must be much less than the weak feedback inverter. So you need to worry about all of these. This will be stronger compared to this one. And the solution, check the relative strength. Avoid unbuffered diffusion inputs where driver is unknown. And one of the troubles that we didn't do, we didn't protect the D. If you protect the D, this one won't happen. Now, the bad circuit number 6. Now the circuit is a domino and gate, as you can see here, and the symptom recharge the gate while A equal to B equal to 0. So Z is equal to 0. Now you set phi equal to 1. A rises and Z is observed to sometimes also rise. So if you rise A, Z also rise, meaning that Y is actually falling down. And the Y is falling down because it's sharing its charge with X. And we talked about charge sharing before. So the principle here is the charge sharing. If X was low, it shares the charge with Y. And one solution is limit the charge sharing. We can calculate the charge sharing by this equation. And I suggest that you go back to our previous talk that we detailed the charge sharing problem and how to solve it. This is safe if the capacitance of the Y is too huge, so it can feed the X and still remain on the level of logic 1. If it is not, then the one solution is actually pre-charged on X2. So you connect PMOS here. And whenever you charge Y, it should be connected to phi as well. Whenever you are charging Y, you charge X as well. This way, X doesn't take anything from Y. Now, the bad circuit number 7 is a dynamic gate with a latch. So it's a dynamic gate with a latch. It's like a terrible latch, but that's one of the old latches. The symptoms here is recharge gate while transmission gate latch is opaque. You evaluate, and when the latch becomes transparent, X fall down. Again, the problem is charge sharing. If Y was low, it charges it shares its charge with X. The solution: buffer the dynamic nodes before driving the transmission gate, or build a regular latch. Now, this is bad circuit number 8. Again, this is the latch. And here we don't have phi and phi bar as the previous example. Here we have ground and VDD. The symptoms: Q changes while the latch is opaque, especially if D comes from far away driver. Again, you are not protecting the D. That's one of the issues. By protecting the D, I mean you need to add an inverter. Now, the principle here, the diffusion input noise sensitivity. If D is less than minus V threshold, the transmission gate turns on, most likely because of the power supply noise or coupling or something away from this latch, because you have no idea D will come from where exactly. So the solution: buffer D locally, meaning adding this inversion, adding this inversion. If you add it, then you'll solve it. In summary, the static CMOS gates are very robust. It will settle to the correct value if you wait long enough. Other circuits suffer from a variety of pitfalls. There are trade-offs between performance and robustness as well. Essential to check the circuits for pitfall, and we give you several examples to practice. For large chips, you need an automatic chip. Design rules, so you need some tool that can help you with this. Design rules aren't worth the paper they are printed on unless you back them up with a tool. And with that, we finished our talk.